Hi, I'm meteorologist Jennifer Perez, and this is What's Up with the Weather. Today we are talking about thunderstorms, how they form, and the different types of thunderstorms that we could potentially see. Now, a thunderstorm is essentially a rain shower that's become strong enough to produce thunder and lightning. And did you know that on average every year there are about 60 million thunderstorms that happen across the globe? Crazy, right? But in order for thunderstorms to develop, we need a specific amount of ingredients in place for it to develop. Just like baking a cake, think about it. You need to mix up all the ingredients in a bowl, and you have to put it in the oven, and it bakes and it rises, right? So you need all those ingredients in place to bake a cake. It's very similar to a thunderstorm. You need a specific set of ingredients. These are the ingredients that you need: moisture, instability, lift, and wind shear, speed and directional wind shear. So as far as moisture is concerned, we're talking about warm, moist air. Okay, so to add moisture, usually that comes from the Gulf of Mexico or the Atlantic Ocean. We look at dew point temperatures to analyze the amount of moisture within the atmosphere. Usually you need dew point temperatures at least 50 degrees, if not higher. Ideal conditions would be 60s for dew point temperatures. Secondly is instability. Okay, instability is the amount of heat energy that piles up at the Earth's surface, and that heat energy comes from the sun, as in solar radiation. And that instability at the Earth's surface is what helps provide heat and energy to fuel our thunderstorms. Then you need lift, a lifting mechanism of some sort. So that could easily be a cold front, a warm front, a cold front, warm front, a dry front, a sea breeze. Think about a sea breeze in Florida. You have winds off of the Atlantic, you have winds off the Gulf of Mexico. They all combine and they clash and they converge in central Florida. That clash forces the air to rise vertically, and then you get thunderstorms. Very typical in the summertime in Florida. So you could get it from a sea breeze or even something we called orographic lift. And so what happens there is you have the warm, moist air that comes off, say, the Atlantic, and it encounters, say, the Smoky Mountains. That air is forced to rise vertically up across the mountain, vertically up. And as it encounters the mountain and the topography of the mountain, friction happens. And because of that friction, the air continues to rise, it cools, and it condenses, and eventually forms a thunderstorm on the windward side of the mountain range. Okay, and then there's wind shear. You need speed and directional wind shear. All of those parameters, you need all of those ingredients in place to trigger thunderstorms. Now let's dive a little bit deeper into a few of those ingredients, like instability. Okay, so instability, basically, stability determines the strength of the thunderstorm. So if you have a stable air at the surface, you're not really going to get any thunderstorms. You're not going to get any cumulus clouds. So the more unstable the air is at the Earth's surface, the more instability you have. And we measure that as meteorologists through a parameter, a form of measurement to be able to tell that, known as CAPE, or convective available potential energy. And we measure that in joules per kilogram. It ranges from weak CAPE to extreme CAPE. And ideally, thunderstorm development, you can see it starting at moderate CAPE, which is at least 1,000 to about 2,500 joules per kilogram, with extreme CAPE higher than 4,000 joules per kilogram. Those are numbers that you tend to see in Tornado Alley, like Oklahoma and Kansas and Missouri. Now, as far as shear is concerned, I mentioned it earlier, but this is a breakdown of shear. Shear actually determines the type of thunderstorm you end up with. There are two types that we need to look for. Vertical directional shear is the first one. And with that one, it just means that winds are changing with height within the atmosphere. Ideally, you would like to see southeasterly winds at the ground In the mid-levels, southwesterly winds, and in the upper levels, westerly winds. So with the change in wind speed with height, that creates rotation within the air. And if you have all other parameters or all other ingredients in place, you could see a tornado develop with that type of wind shear environment. Then there's vertical speed shear. This is the second type of shear in place, also to help trigger thunderstorms. What this one is essentially you have winds from the same direction at all heights. So from the ground to the upper levels, generally from the same direction. So for the most part, westerly winds from the ground all the way up to the upper levels. And within that, we also see the winds increase as you go vertically up within the air as well. So now that we've talked about thunderstorm ingredients, those are all the ingredients that you ideally need to have a thunderstorm to develop and certain types of thunderstorms to develop. But this is the life cycle of a thunderstorm. It starts off in the cumulus stage. It's stage 1. And that's when you have warm, moist air rising up, and that warm, moist air and that water vapor cools and condenses and forms into a big cumulus cloud. At that point, you have the warm, moist inflow dominating. That's what we call an updraft. That's stage 1. In stage 2, that storm gets vertically larger, right? You get this towering cumulonimbus cloud that develops. You have the updraft, which is that warm, moist inflow air that allows energy to rise up into the thunderstorm and continue to fuel it to stay strong and healthy and keep going. At that point in time, we also start to see that thunderstorm produce precipitation. And when that happens, we get a flow of rain-cooled air from the top of the cloud all the way towards the ground surface. This is what we call a downdraft. So both of these exist within the mature stage, an updraft and a downdraft. And then finally, the third stage within the life cycle of a thunderstorm is the dissipating stage. This is the point where it's at its weakest. At this point, the downdraft, that rain-cooled air, dominates within the thunderstorm, and it cuts off the updraft. It cuts off the warm, moist inflow air that keeps the thunderstorm alive. And so it mainly ends up being just rain at that point in time, and the thunderstorm continues to weaken. So that's the life cycle. But there are several different types of thunderstorms. Okay, so we'll go ahead and break them down. The first type of thunderstorm we could potentially see develop is a pulse type storm, or otherwise known as a garden type variety of thunderstorm. It's very common in the summertime. Usually, the ground heats up, you have the warm, moist air that rises, you get the cumulus cloud that develops, and in the summertime, during the afternoon, the towering cumulonimbus cloud develops. You get eventually rain that comes down, and it weakens and it ends rather quickly. Okay, so the life cycle, the time span of the life cycle of a pulse-type thunderstorm is short. It's very short-lived. It doesn't last very long. The second type of thunderstorm we get is something called a multi-cell cluster. Okay, this is where there are several different cells clustered together, and they all feed off of each other. They all feed off of each other's energy. For example, cell 1 is in the dissipating stage of the thunderstorm. At this point, we just have rain-cooled air, the downdraft. It just dominates. It comes from the top of the cloud towards the Earth's surface. That cool air pushes the warm air at the surface up vertically and helps initiate and trigger cell number 2. Cell number 2 at this point is at its healthiest stage, the mature stage. And that's at this point where we have the warm, moist inflow air, the updraft, and the downdraft existing all at the same time. It's the healthiest one and the strongest one. The downdraft within this cloud, or within this cell 2, that cool air that's coming down to the surface, also helps trigger the development of cell number 3. It helps rise or helps increase and vertically rise the warm, moist air at the surface, developing cell 3, and so on and so forth. So you kind of get the idea, right? Now, this type of thunderstorm is very common in the western plains, and they tend to develop very late at night, and they continue strong during the overnight hours, eventually decaying and weakening by dawn of the next morning. So it's usually an overnight type of thunderstorm. But also going in line with multi-cell storms is another category, the multi-cell line. Very similar to the one I just mentioned, except that the shape of it is a linear shape, okay? So it's generally more of a line of thunderstorms. You've probably heard of a term called squall line. That's what this is. It develops in front of a cold front, all right? And if it gets stronger, we could see it eventually turn into something called a bow echo, or a line echo wave pattern, or a derecho, all of which in those events are stronger, with the main hazard at that point in time being damaging winds within that within the multi-cell line and within those types of thunderstorms. And finally, probably the most iconic type of thunderstorm, probably the one you might think about, right, in Tornado Alley, is the supercell type of thunderstorm. There's a lot of stuff happening here, but this kind of shows you the depiction of what it looks like. So within the supercell, first off, the wind flow. You have vertical directional wind shear in place. So again, we have the changing in wind direction with height. At the surface, we have a southeasterly wind bringing in the warm, moist air, which helps provide fuel for the thunderstorm to continue to stay healthy and to continue going. In the mid-levels, you have a southwesterly wind, and that brings in a little bit more of drier air. In the upper levels, you have westerly winds in place. And all of these combined help create rotation within the thunderstorm. Eventually, if it gets strong enough, you get a rotating updraft. So the inflow of warm, moist air rotates within the thunderstorm, within the supercell thunderstorm. You also have two downdrafts, two areas of cooler, relatively cooler air. The forward flank downdraft of rain-cooled air and the rear flank downdraft. Now, the rear flank downdraft is generally a little bit warmer as compared to the forward flank downdraft. But also, some other features that you'll notice if you see a supercell is the overshooting top, and that's just a sign of how strong it is and where that updraft is located at. And you'll also see the anvil cloud top that you'll see. You'll also see the cumulonimbus clouds within it and the flanking line of clouds coming up behind it. Okay, this is a very strong type of setup, a strong thunderstorm type. If it gets stronger, we could eventually see something called a wall cloud develop from the base of the cloud. You get a lowering within the cloud cover. And at that point, as it gets closer towards the ground surface, at that point with added rotation at the surface, we could potentially see the development of a tornado. And the setup for a supercell to potentially develop goes like this. So this is how it looks, and when we combine all of the ingredients we talked about in place at the surface. So what you have is the area of low pressure, so the storm system. This is set up for the Central Plains in Tornado Alley, where we tend to see the supercells develop. But you have very warm, moist air coming in from the Gulf of Mexico, pretty much behind the warm front. You have a dry line in place, so a dry front. So behind the front, you have drier air coming off the Mexican plateau, and that's going into the mid-levels of the thunderstorm. And then you have the cold front behind the front. So you end up seeing air that's cooler and more dense, air that's coming from the northwest behind that cold front. All of these combined with all of the ingredients I mentioned before could potentially produce a severe weather outbreak. Again, it all depends on how things set up, all the ingredients and how they set up. But usually for supercells to develop, this is the basic setup for that as far as the fronts and air masses are concerned. So that covers thunderstorms, thunderstorm formations, and thunderstorm types. Here in the UP, we don't tend to have long track or violent tornadoes. We do get thunderstorms during the summertime. We have had some supercells develop from time to time. It's not a huge common feature as compared to Tornado Alley. They again tend to get the long track violent tornadoes. If we do end up seeing a tornado from a severe thunderstorm, they generally trend to be the weaker ones. So those would range in the range of an EF0 to potentially an EF2. It's not very common, but on average, we average about 1 tornado every year in the UP. So that does it for thunderstorms, thunderstorm formations, and thunderstorm types. Next up is lightning.